So we've been alluding and talking about yields of reaction. There's really sort of three types of yields that we come across in a reaction. One is the theoretical yield. And by the way, if it is a yield, it needs to be a product. So reactants aren't yields. So only products give you yields. And again, the theoretical yield is based on the limiting reagent in the reaction. So the theoretical yield is the amount of product that you should produce in a reaction based on the balanced equation and how much you're starting with of the limiting reagent. It should really be your maximum yield. So, whatever you weighed out, for example, to do that last experiment in the solid was your starting amount, and that would give you your theoretical yield. The actual yield is pretty much what it sounds like. It is actually the amount of product that you made when you did the experiment. So obviously in the lab, that would be how much you made as a result of the experiment. In book problems, that is typically given to you. So usually that is given to you in book problems. And the theoretical yield and the actual yield is useful because that will allow us to calculate what is commonly referred to as the percent yield. And the percent yield is to take the actual yield divided by the theoretical times 100%. Now, when you're dealing with percent yield, you want a high number. You typically don't want over. If you get over 100%, frankly, you screwed up somewhere probably. Yeah, it's usually the reason why you got over 100%. For example, the experiment the other day, you filtered it through filter paper, and that filter paper is wet. So if you didn't let it completely dry and you reweighed it, you would have a lot more mass that's actually water than your product, and it would get you a greater actual yield than theoretical yield, and you'll get over 100%. Over 100% yield. A lot more water they shouldn't have, but you typically don't want to get over 100% yield, but higher number is good. 95, 96, 97, and 90s. Those are really, really good. A very small number for percent yield is not so good. That means you kind of lost a lot of stuff along the way, which you don't want. Now, how do we get the theoretical yield or actual yield? Again, the actual is typically given to you in the problem. Theoretically, you typically need to calculate. So why don't you give it a go here in this reaction? We take 2.46 times 10 to the 4 kilograms of TI. Yeah. A yield because it's really based off of like an equation. When we talk about an equation, the arrow, right? We have our reactants, we have our products, and really the arrow means to yield. So it means that's why we call it a yield. Is basically we take those reactants, they come together, and they yield these products, and that's how much of the products that you make. That's why a yield should always be a product. It cannot be a reactant. Yep. All right, so why don't you give this a go here and see what you come up with. We take 2.46 times 10 to the 4 kilograms of TiCl4. Molar mass from the periodic table, 189.7 grams per mole. And magnesium's molar mass, 24.31 grams per mole. What is the theoretical yield in kilograms? And if we produce 5.42 times 10 to the 3 kilograms of TI, what is the percent yield? It takes a few minutes to do that. Remember, there are 1,000 grams in a kilogram. Yeah. Okay, let's take a look and see how you're doing here. So once again, we got a couple of things going on. We're looking for the percent yield. And once again, our percent yield going to be our actual divided by our theoretical times 100%. In the problem, we were given the actual, which is that number right there. So we do need to figure out the theoretical here. So we need to do a stoichiometry problem. Once again, here we're given actually the starting amounts of both reactants in kilograms. which means we can go to grams and also go to moles for each of them. So this, once again, is a limiting reagent problem because we can get the moles of both of our reactants. So we have an equation. It's balanced. Like we want to start all stoichiometry problems. We're going to convert everybody into moles here. So we got one extra conversion to kind of get it into grams and then to moles. So 2.46 times 10 to the 4 kilograms of TiCl4. There is, once again, in a kilogram, 1,000 grams. Now that I have it in grams, I can use the molar mass from the periodic table, which in this case is 189.7 grams per mole. So I'm just adding this sort of extra step to get me to grams so that I could then get to moles, making sure you use your exponent button. We're going to end up here with a number. We'll call it 1.30 times 10 to the 5th moles of TiCl4. We're going to do the exact same calculation here for our magnesium. We're going to take our starting amount in kilograms. We're going to convert our kilograms into grams. And now that I have it in grams, I'm going to use the molar mass of Mg from the periodic table, 2431 grams per mole here. That gives me 1.44 to the 4th times 1,000 and divided by 2431. And that'll get me 5.92 times 10 to the 5th moles of magnesium. Any questions on that so far? So just like we've been doing, I'm just going to grab one of the reactants and again do a calculation to figure out how much of the other reactant is needed to use it up. So in this case, I'm going to try to figure out how much magnesium is needed. So basically, how much magnesium is needed to use up all of the TiCl4. So starting with my starting amount of TiCl4, from the balanced equation, it is a 1 mole, which is the coefficient, to 2 moles for the coefficient for magnesium. So we're going to use the stoichiometry here to do that. 1 mole of TiCl4 gets me 2 moles of magnesium. The moles of that guy cancels. Gets me 1.3 to the 5th times 2. Gets me 2.6 times 10 to the 5th moles of magnesium is needed in this case. Once again, once I figure out how much is needed of one reagent, I am going to compare it to my starting amount, which are these guys here. So I need 2.6 to the 5th moles of magnesium. I have 5.92 times 10 to the 5th moles of magnesium. Do I have enough in this case? I do. So because I have enough, once again here, that would mean the magnesium would be our excess reagent. And the TiCl4 would be our limiting reagent in this case. Once again, we do need to determine the limiting reagent because that is going to determine how much product we make, which is what we're ultimately after. So we're going to take the starting amount of our limiting reagent and now actually do the calculation to figure out our theoretical yield. So we got moles of TiCl4. We now want the relationship between TiCl4 and our product, which is Ti. And from the equation, it is a 1-to-1 relationship between those two. So that makes it not too bad. A mole of TiCl4, a mole of Ti. Moles of TiCl4 end up, and we end up with 1.3 times 10 to the 5th moles of Ti. Now, that would be technically the theoretical yield in moles. I probably want my end theoretical yield to be in what units? They should probably end up being in kilograms. So everything kind of cancels out correctly. So I'm going to do those two conversions right here. I'm going to use the molar mass from the periodic table for Ti. which would be 4788 grams per mole. Those cancel. And since I want it in kilograms, I'm going to do 1,000 grams in a kilogram just to get me again into the right units here. So taking 1.3 to the fifth times 47.88 divided by 1,000. Like I missed a number there. Try that again. 1.3 to the fifth times 47.88 and divided by 1,000 here. That is going to get me here 6.22 times 10 to the 3 kilograms of TI. That would be my theoretical yield. Any questions up to there? Now that I have the theoretical yield and I have the actual yield that was given to me, I can now calculate the percent yield. Percent yield would be our actual, which I kind of scribbled over, but I think it says 5.42 times 10 to the 3 kilograms divided by our theoretical 6.22 times 10 to the 3 kilograms times 100%. And that's going to give me looks like 87.14%. Not too bad. Percent yield in this case. Yeah. Any questions on any of those steps? Yeah. You could. So you could have done kilograms, the whole problem. You just want to make sure you're not off by any type of factor. The other sort of question similar to that is in terms of calculating percent yield, it doesn't necessarily have to be grams and grams. It could be kilograms and kilograms like we did here. You could also calculate the percent yield using moles and moles. So as long as the percent yield calculation, both the theoretical and the actual are in the same units, you could calculate the percent yield. It doesn't necessarily have to be grams. Yeah. 47.8. Are we talking about this number or when I was converting, say one more time? For the theoretical, this number right here, that's the molar mass of TI for the periodic table. Yeah. Yeah. Other questions? Yeah. High percent yield means, for lack of a better word, you did the experiment good. There wasn't a lot of side reactions. You didn't lose a lot of product along the way when you did the reaction. And that's usually what you want to go for. Sometimes people hear percent yield and get confused sometimes with percent error. Percent error is, how good or bad you did it. In percent error, you want a really low percent error when you do something. But percent yield, you typically want a high percent yield, not above 100. But it gives you how good sort of the experiment went. And again, if you think about maybe the experiment did the other day, it makes this yellow solid and you stir it with your stirring rod. A lot of the yellow solid stays on your stirring rod, maybe doesn't get back onto the filter paper. A lot of the yellow solid stays over in the beaker, doesn't get onto the filter paper. So those are all places along in a normal sort of process of doing an experiment that, you just lose a certain amount of product based on just doing the actual part of the experiment. In addition to anything that you might have screwed up on, you get a worse percent yield. Other questions? Let's try one more here to wrap it up. All right, we do this reaction here. We start with 100 grams of ammonia, reacts with 100 grams of carbon dioxide, and we produce 120 grams of our product. What is the percent yield? Nitrogen is 1401. Carbon is 12.01. Hydrogen 1.008. Oxygen here 16. By the way, just to help you, since we're getting to the end, we did ammonia earlier. Molar mass is 1703 grams per mole. And CO2 is 4401 grams per mole. We used those in previous problems. The time, there you go. Okay, let's take a look at this. So once again, we do know that this is a limiting reagent problem because we are given the starting amounts of both our reactants, and that means we can get some moles of each of those. So that's where we're going to start with here. We're going to take the 100 grams of ammonia. We're going to use the molar mass of ammonia from the periodic table, 1703 grams per mole. We're also going to take the 100 grams of CO2. Use the molar mass from the periodic table, 4401 grams per mole. That is going to give us 100 divided by 1703, 5.8720 moles of NH3. 100 divided by 4401, 2.2722 moles of CO2. Once again, we're going to do our calculation to figure out which one is the limiting reagent. So I want to know how much CO2 is needed in this case. So basically use up all the NH3. So I'm going to start with my NH3, which is 5.8720 moles. Using the mole-to-mole relationship from the equation, it's a 2-to-1 relationship. 2 moles of NH3, 1 mole of CO2. Then we're going to divide that by 2. 5.8720 divided by 2 tells us we need 2.936 moles of CO2 is needed. Remember, this is our starting amount. So we're going to compare those two, and we do not have enough. So in this case, that means that the CO2 is the limiting reagent, the NH3 is the excess. So now that we got the limiting reagent figured out, we're going to, I'm just going to get rid of some of this stuff here to write on. Give me one sec here. Get rid of those guys here, a little bit there, a little bit there. Now that we have the limiting reagent, what we're going to do is use the limiting reagent's the starting amount to figure out how much of our product we're going to make. So in this particular case here, we're going to take 2.272 moles of our CO2. We're going to do a mole-to-mole relationship between the CO2, our limiting reagent, and our product, which is a 1-to-1 relationship from the coefficients. 1 mole of CO2 gives us 1 mole of our product here. Those guys are going to cancel, giving us 2.2722 moles of our product. Using the molar mass, which I just erased, was 6006, I believe. We're going to convert that into grams of our product. So using the molar mass of 6006 grams per mole, that's the molar mass of our product here, will get us 2.2722 times 6006, a theoretical yield of 136.5 grams for product here. And that is our theoretical yield. Now, our actual yield was given to us in the problem, which I kind of forgot, which I think was 120 grams. So our actual yield was given to us in the question, which was 120 grams. So to calculate our percent yield, we will take our actual 120 grams divided by our theoretical of 136.5 grams times it by 100%. gives us a percent yield here of 87.91%. So once again, here to solve these problems, you'd use our basic stoichiometry steps, or if it's a linear agent, our linear agent steps to figure out the theoretical yield, and then to calculate the percent yield, take the actual divided by the theoretical times 100%. All right, that should wrap up chapter 9. And we'll wrap it up there for today.